Hi, this is the video for section 4.5, the final section of chapter 4 of A Student's Guide to the Schrödinger Equation. This one's about position and momentum wave functions and operators, but it also gets into the Heisenberg uncertainty principle and what's called the canonical commutation relation between the position and momentum operators. The previous section talked a lot about Fourier transform relationship between position functions and wave number functions, but in quantum mechanics you're more often going to be dealing with momentum rather than wave number. You know how those are related. The de Broglie relation tells you that P is h bar k, and here's how we define phi tilde of P. That is the momentum spectrum that is related to the position function through the Fourier transform. Notice that this equation resembles the equation for phi of k, but we've plugged in p over h bar, where k was in this exponential, and we've inserted a factor of the square root of h bar in the constant out front. The inverse Fourier transform is what you'd expect. Now we have phi tilde of p here, the positive exponential still with p over h bar in it, and our square root of h bar term also appears in this constant. But if you just take our expression given in equation 415 for the inverse Fourier transform, and you plug in k is p over h bar and dk is dp over h bar, you would get an expression that looks like this. There's where our k went, there's our dp over h bar. And why have I shown you this? Well, if I clean this up, you can see that our definition for the inverse Fourier transform involving momentum differs from this, because we have a square root of h bar in the denominator of the constant, whereas this is going to produce an h bar. So what we've done is we've absorbed a factor of the square root of h bar into phi tilde of p, and the other square root of h bar we insert in the constant here. That's how the majority of quantum texts handle this. There are some popular texts that absorb the entire 1 over h bar from this expression into phi tilde of p, and in those texts, you won't see this factor of 1 over the square root of h bar in the definition of the forward and inverse Fourier transform. Their constant will just be 1 over the square root of 2 pi. Okay, but whether you absorb the entire h bar or the square root of h bar into phi tilde, the important point is that the Fourier transform relationship between the position and momentum wave function leads to the Heisenberg uncertainty principle. So that's the first thing we're going to address in this section. Now, the uncertainty principle exists for any Fourier transform pair, so we could use our phi of k and sine of ax over ax position wave function, but remember that sine x over x had all those minor lobes extending out in position space, and our goal, after all, was to localize our position wave function, and a good way to do that is to use a Gaussian wave packet. So does that mean Gaussian in position space or Gaussian in momentum space? Good news is it's Gaussian in both. And you can understand that by starting with the expression of a Gaussian, which has some amplitude, capital A. This term is the distance from the center of the Gaussian function, which is at x0, and sigma sub x is the standard deviation, which is the half-width of the function at about the 1 over the square root of e points. That is about 61% of the way down from the maximum value. A couple of handy features of Gaussian functions are talked about here. The square of a Gaussian is also a Gaussian, and the Fourier transform of a Gaussian is also a Gaussian. Those are useful in quantum mechanics because probability density is related to the square of the wave function, and position and momentum space wave functions are related by the Fourier transform. The advantage of a Gaussian wave function can be seen in this figure. Notice here we've got a rectangular wave function compared to a Gaussian wave function in momentum space, and look at the difference in position space. These are those extended lobes that I talked about that are needed because of these corners in the rectangular function. Without those, we proceed smoothly downward here in the Gaussian function. It takes longer to get to 0 than the rectangular function, but you gain the benefit of losing those minor lobes. So what does that Gaussian wave function look like? Here it is written out. This is the Gaussian part. That's the envelope, if you will. Amplitude A, this is the Gaussian shape. And this factor is the complex sinusoidal oscillating factor. It was e to the I k0x. In the wave number case, here we write it as e to the I p0 over h bar x. But it serves the same function. There's a note here that says you should be aware that sigma sub x, as we're using it here, represents the standard deviation of the wave function, psi of x, which is not the same as the standard deviation of the probability distribution, which you get by taking the square magnitude of the wave function. More about that later. As with any quantum wave function, good idea to make sure it's normalized. We can do that by setting 1 equal to the integral of psi star psi over all of space. Here's psi star, here's psi. Notice that the complex conjugate puts a minus sign in front of the exponent with p0 in it. So that shows up here, and that means that that term goes to 1, and we're left with this. Looks like kind of an ugly integral, but it's not too bad because we've got this handy integral identity, which says if you've got this quadratic exponential, and you integrate over all space, you get this. So here are what those ABC constants equal in our case. When you plug them in and do a little simplification, you get this. So solving for A, we find that it's 1 over the square root of sigma x times the square root of pi. If we plug that in, our normalized wave function becomes this. So again, constant out front sets the amplitude, Gaussian envelope, and complex sinusoidally oscillating term. So what does the momentum wave function phi tilde of p look like for this psi of x? We know how to do that. We're going to take the Fourier transform of psi of x. That looks like this. So for psi of x, we plug in our expression. That goes in here. Gathering the constants out front, we're left with this, which again looks pretty nasty, but it's got an x squared term and an x term, no constant term. So we can use that same definite integral with this a and b and c equals 0, and that makes phi tilde of p look like this. We plug in our a, b, and c values here, and it simplifies to this. So is this a Gaussian? Well, sure it is. It's got an amplitude term, an exponential, with this minus p0 quantity squared. But instead of 2 times sigma sub p in the denominator, we've got 2 times h bar squared in the denominator and a sigma sub x squared in the numerator. But that's okay. We can make that into a Gaussian with sigma sub p squared in the denominator, as it should be, if we simply set sigma sub p equal to h bar over sigma sub x. So our h bar squared in the denominator and sigma sub x squared in the numerator simply become sigma sub p squared in the denominator. And that leads to an interesting result. If we multiply sigma sub x times sigma sub p and plug in sigma sub p as h bar over sigma sub x, we just get h bar. So is this the Heisenberg uncertainty principle? Almost. The Heisenberg uncertainty principle is defined with respect to the standard deviations of the probability distribution, and those are narrower than the width of the Gaussian wave function, psi of x and phi tilde of p. That's because the product of two Gaussians is also a Gaussian, so we'll write the probability density function as a Gaussian with standard deviation delta x. Set that equal to psi star psi, plug in psi star, plug in psi, and when you multiply those, you add the exponents, and you get this. So when you compare those, you find that 2 delta x squared, that is 2 times the standard deviation of the probability distribution squared, is equal to the square of the standard deviation of the wave function. Or sigma sub x is the square root of 2 times delta x. You can make that same argument for momentum, and sigma p is the square root of 2 times delta p. There's a little note here that this explains why some authors and some instructors will define the Gaussian wave function as having a 4 in the denominator rather than a 2. They're writing sigma sub x as the standard deviation of the probability distribution rather than the standard deviation of the wave function. But that's okay. Whichever way you do it, when you multiply the standard deviations of the wave functions, which are these for the probability distributions, you get h bar, and if you solve that for the widths of the probability distributions, you get h bar over 2. So is this the Heisenberg uncertainty principle? Almost. We achieve this result using Gaussian wave functions. If you had used any other wave function, you would have found that delta x, delta p, that is the width in the position and momentum domains, is greater than h bar over 2. So the Heisenberg uncertainty principle is written with greater than or equal to h bar over 2, in which the equal sign applies to Gaussian wave functions. And it doesn't just hold for position momentum. It holds for any pair of conjugate or incompatible observables. Precise knowledge of one, such as momentum, that is small delta p, means that you cannot have precise value of position, that is small delta x. That's the nature of the uncertainty relation. And as it says in this paragraph, another important aspect of observables which are incompatible is that the operators associated with those observables do not commute. So the order in which those operators are applied makes a difference in the result. We're going to talk about that for the position and the momentum operators, and it's a good idea to understand what those operators look like both in position space and in momentum space. So that's what's up next. In discussing these operators, I'm going to address 4 questions that, it's been my experience, students new to quantum mechanics often have. The first and the third deal with operating on a position wave function with the position operator and operating on momentum wave function with the momentum operator. The second deals with the form of the position functions in position space, and the fourth, the momentum eigenfunctions, also in position space. So the rest of this section is going to address those questions. A good way to start off is recalling from section 2.5 that the expectation value of a variable such as x, this is a continuous variable, so we see the integral of x multiplied by the probability density function p of x and integrated over all space. This is the continuous version of multiplying each possible outcome by the probability of that outcome and then summing those results. We also know that for normalized quantum wave functions, the probability density is given by the square magnitude of the wave function, psi star psi, so we can write the expectation value like this, where we've substituted in the square magnitude for the probability density function, or by writing the square magnitude as psi star psi, making the integral with the variable x in between, the complex conjugate of psi and psi. But we also said in section 2.5 that the expectation value for any observable x which has an operator x hat for a given wave function psi can be found from this expression, which we said is a form of the inner product, and here's what that looks like when you write it out as the inner product for a continuous function. Now compare these two. It'll help if I clean this up a little bit. Here we have 2 expressions for the expectation value. Both involve integrals over all space. Both have complex conjugate of psi, but look at this expression. Here we have x multiplying by psi of x, and here we have the x hat operator operating on psi of x. That means that operating on psi gives the result of multiplying psi by x. And it explains here, that's because the operator's job is to pull out eigenvalues from the eigenfunctions of that operator. You can read about that in section 4.2. So the possible results of position measurement are every position x, so that's what the x hat operator pulls out of the eigenfunctions. So that's why operating on psi of x with the position operator x hat is the same as multiplying psi of x by x. But what are those eigenfunctions of the x hat, that is the position operator? To understand that, write the eigenvalue equation. We know that x, operating on the first eigenfunction, call it psi1 of x, produces the eigenvalue associated with that eigenfunction, x1, multiplied by psi1 of x. That's just the eigenvalue equation. But what we said above was that operating on a position function psi of x with the x hat operator was the same as multiplying that function by x. So both of these are valid expressions for what happens when you operate on psi1 of x with the x hat operator. That means their right sides must be equal, and it's written down here. That says that x times psi1 of x is equal to x1 times psi1 of x. And if you think about it, that's a pretty strange equation, because x can take on any value at all in position, but x1 is a specific position. It's the eigenvalue associated with the first eigenfunction. So how can those two be equal? The answer is given down here. The function psi1 of x must be 0 everywhere except at the single location where x equals x1. Why is that? Well, think about what happens if this psi1 of x is 0 everywhere except at x equals x1. Then whenever x equals anything but not x1, then this side is 0 because psi1 of x is 0, and this side is 0. So the equation is true. But what about when x does equal x1? Then you've got x1 here for x, and you've got x1 on this side, and the equation is still true. So this equation can be true if psi1 of x is 0 everywhere except at x equals x1. Well, you know what that is. That's the Dirac delta function, delta of x minus x1. And for the second eigenfunction, psi2 of x, if it has eigenvalue x2, then that function must be delta of x minus x2. and for the third eigenfunction, delta of x minus x3. So since this is a continuous variable with an infinite number of eigenfunctions and eigenvalues, you can write the general expression that the eigenfunctions of the position operator are simply delta of x minus x prime. So that's why, in position space, the position eigenfunctions are delta functions. By the way, this also works for momentum operators and their eigenfunctions in momentum space. So you can go through the same kind of analysis and say the expectation value of momentum is p multiplied by the probability, which is phi tilde of p squared, the momentum basis wave function. And we can write that out just like we did for the position case. And we can say, but that also must equal this expression, in which case the p hat operator with the subscript p tells you that this is a momentum operator. That's what the p wearing the hat is. And the lowercase p in the subscript says this is the momentum basis version of that operator. So that is what's going to operate on momentum functions. Just like we did for position space, we can then set the p operator result operating on the momentum eigenfunctions equal to momentum times those functions, which must also be, for the first momentum eigenfunction, p1, the eigenvalue, times phi1 tilde of p. And using that exact same analysis, that says that in momentum space, the momentum eigenfunctions must be an infinite set of direct delta functions, delta of p minus p prime, just like we had delta of x minus x prime in the position case. And this is a general result. In any operator's own space, since the operator must act on its eigenfunctions by multiplying that eigenfunction by the observable corresponding to the operator, those eigenfunctions must be direct delta functions in the space of the operator. So in position space, the eigenfunctions of the position operator are delta functions, and in momentum space, the eigenfunctions of the momentum operator are delta functions. But sometimes you want to apply an operator to functions in other spaces, like applying the momentum operator to a position wave function. So we're going to need a position space version of the momentum operator. It explains here why you might want to do that. Maybe you've got the position basis wave function and you want to know, okay, what's the expectation value of momentum? You can get that, writing that expectation value with the momentum operator, the x means position-based version, operating on the position wave function. So what does that momentum operator p hat look like in position space? Well, we know that the momentum space eigenfunctions of the momentum operator are these delta functions. So let's use our inverse Fourier transform to see what those functions correspond to in position space. Here's psi of x. We're going to plug in our delta function for phi tilde of p. That's shown here, but you know what a direct delta function does when it's inside an integral. The only place this is non-zero is when p equals p prime, so we can walk this function right out of the integral as long as we plug in p prime, as we've done here. Remember, p prime is a continuous variable, can represent all possible values of momentum. We may as well call that p instead of p prime, and that means that in position space, the momentum eigenfunctions look like this, which is exactly what we'd expect. They're the wave functions of plane waves. And you can use those eigenfunctions to figure out the form of the operator. Why? Because the momentum operator in position space operating on the momentum eigenfunctions in position space must simply produce momentum times those same eigenfunctions. Well, if we take our psi of p from up here and plug it in, that looks like this. So the momentum operator in position space operating on this eigenfunction must pull out a p. And how's it going to do that? Well, there's a p up here in the exponent, so maybe taking a derivative with respect to x will work. Let's try that. Here we take the derivative with respect to x of our momentum eigenfunction in position space, and that does in fact pull out a p. Unfortunately, this I and this h bar also come out. We do get the function back exactly as we needed for our equation. Okay, we're almost there. We just need to multiply both sides by h bar over I. That looks like this. And this h bar cancels that one, and that I cancels that one. And now, if we operate on this momentum eigenfunction, position basis version, with this operator, h bar over I, partial with respect to x, look at what we get. P times that eigenfunction. Exactly what we needed. So this must be our momentum operator in position space. Now it's got an I in the denominator, and you can always bring that up to the numerator by adding a minus sign. So there we have it. The momentum operator in position space is minus IH bar partial with respect to x. By the way, you can use this same approach to determine the form of the position operator x hat and its eigenfunctions in momentum space. You find that those eigenfunctions look like this, and the position operator looks like this. Again, both of these are in momentum space. If you want to see how that works, there's a chapter end problem that deals with this, and the online solutions will show you how that works if you have trouble getting it. Okay, now that we know the form of the position and momentum operators, x hat and p hat, look at what happens when you form the commutator. Remember what this is. You multiply the first by the second, and you subtract the second by the first. So I've plugged in the x from the x hat operator and the negative IH bar spatial derivative from the momentum operator. Same thing here, and this is extremely dangerous. Lots of times when people new to quantum mechanics look at this, they go, well, that's just one. But remember, when you're evaluating how operators work, it's really helpful to feed them something on which they can operate, like a function psi. So here's that psi, and when it moves inside and gets distributed, there's a term that's pretty straightforward. But this one, we've now got a product in this derivative, which means we've got to take the derivative of the first term with respect to x and multiply it by psi, and then take the derivative of psi with respect to x and multiply that by x. That's shown down here. When you work through, you find that the first term from here cancels this term, and you're left with this. There's a minus minus, that becomes a plus, and you get IH bar times psi. So the commutator operating on psi gives you IH bar psi. Another way to write that is that the commutator equals this. This is a really important result in quantum mechanics. It's called the canonical commutation relation. Since it's not zero, the position and momentum operators are non-commuting. That means the order matters because they don't share the same eigenfunctions. And remember what happens. If you make, for example, a position measurement of a quantum observable, that causes the wave function to collapse to an eigenfunction of the position operator. But since the position and momentum operators don't commute, that's not an eigenfunction of momentum. So if you then immediately make a momentum measurement, the wave function, which is not in an eigenfunction of momentum, collapses to a momentum eigenfunction. That's a different state of the system, and the position measurement you made is no longer relevant. That, in a nutshell, is quantum indeterminacy. Okay, you're going to see 3 specific potentials in the next chapter, but I strongly recommend, as I have in every chapter, before moving on, work through these problems. The solutions are available on the app and on the website, and I guarantee you will have a deeper level of understanding if you attempt to work these problems before moving on. Good luck with that. I'll talk to you in Chapter 5.